What is a microgrid? A microgrid is an electrical power system which contains at least one distributed energy resource, or DER. These DERs include distributed generation and distributed storage. Distributed generation includes renewable energy generation such as solar panels, wind turbines, or geothermal, as well as non-renewable generation such as combustion engines, turbines, microturbines, or fuel cells. Distributed storage includes energy storage technologies such as batteries, flywheel storage, or new emerging technologies. A microgrid requires the ability to form an intentional island from existing electric power systems, or EPS. This means that loads and energy sources connected to the microgrid can be disconnected and reconnected automatically. This can improve reliability and power quality conditions for loads connected to the microgrid. Our proposed microgrid will be at UB North Campus. Figure 1 demonstrates existing generation locations on UB North Campus. Existing generation sites include multiple solar arrays as well as microturbines on top of Alumni Arena. Figure 2 demonstrates the existing property lines with SBL number 55.01-1-1. At a minimum, our microgrid will be required to include parallel grid-connected and intentional island modes, resilience to forces and natures in Buffalo, black start capabilities, and it will maintain voltage and frequency in accordance with ANSI C84-1 standards. In the emergency intentional island mode, the microgrid will only serve critical facilities such as residential, food service, public service, and emergency shelter locations. The microgrid will also automatically disconnect and reconnect from local area EPS national grid during this emergency island. In Buffalo, the only force of nature that will affect generation is snowfall covering our solar panels, which can be fixed easily by removing the snowfall. Black start capability for loads connected to the microgrid will be supported by energy storage through battery technologies.
All existing wiring that powers UB's facilities are buried underground, and the implementation of the new design will include burying the new wiring while tapping into the existing infrastructure. Moreover, several battery containers will constitute our storage system, and they will be used to provide 480 volts to all the microgrid's connected loads. The specifics as to how power is delivered to these loads is a function of whether the microgrid is operating under normal procedures or emergency procedures. The operation of the microgrid is split up into two sets of operating procedures. The first is how the microgrid will function under normal operations. And during normal operations, the microgrid will first function to charge its battery storage system. Following full charging, the grid will offer ancillary services. Such capabilities permit the system to sell excess power to energy providers for revenue. It permits voltage support during brownouts, and it creates the ability to power loads that require large surges of power to start up. The second set of procedures relates to how the microgrid will function during emergency situations. The grid can lose power from an array of events, whether it be from transmission issues or problems caused by severe weather, or any similar scenarios. Under such a scenario where there is a grid-wide outage, the energy storage system will be used to power the most critical facilities on campus, including all of the living quarters, alumni arena, and the student center.
This slide demonstrates key information and characteristics about the loads connected to the microgrid. When in parallel grid-connected mode, the entire UB North Campus will be supported by the microgrid in parallel with National Grid service. The average load for the entire campus is 27 megawatts, with typical peak loads at 23 megawatts in the summer and 32 megawatts in the winter. The campus consumes about 142 million kilowatt hours throughout an entire year, with an estimated 11.8 million kilowatt hours per month, or 2.7 million kilowatt hours per week. While in emergency island mode, about 39.33% of campus consumption will be supported by the microgrid. The average load for this island mode is about 10.62 megawatts, with typical peak loads at 9.05 megawatts in the summer and 12.59 megawatts in the winter. An estimated 55.7 million kilowatt hours will be consumed annually, which equates to 4.6 million kilowatt hours per month and about 1 million kilowatt hours per week. This is the breakdown of our microgrid by sector type. As shown in the table on the left, in parallel grid connected mode, the microgrid will support all existing electrical loads with consumption broken down as 55.75% institutional, 20.26% residential and dormitory, 4.79% food service, 9.08% public service, 6.72% campus service, and 3.4% unmetered locations. When emergency island mode, the microgrid will only support critical locations with a consumption broken down as 13.22% institutional, 51.51% residential and dormitory, 12.17% food service, 23.10% public service, and campus service and unmetered locations will not be serviced in emergency mode. The table on the right shows all of the locations which will be connected while in emergency mode. This covers all residential and food service locations as well as important public service locations. Alumni Arena is also included in emergency operations as a critical meeting location.
UB currently has 5 generation sources on campus, most of which are PV solar arrays. Over 25,000 solar panels across campus account for the majority of UB's power generation. Peak generation is about 7,700 kilowatts, 73 kilowatts from the Norton solar array, 750 kilowatts from the Solar Strand array, 120 kilowatts from the Alumni Arena microturbines, 1,744 kilowatts from the Bizzer Creek arrays, and 5,000 kilowatts from the Amherst Bike Path array. The newly built solar arrays are estimated to add 11.2 million kilowatt hours of production per year, bringing the total solar power production of UB to 11.6 million. These solar arrays cover 34.1 acres of campus, with the largest array along the Amherst Bike Path covering 24.5 acres and containing 16,770 panels. UB is also continuously working with Solar Liberty on the possibility of adding solar panels to the rooftops of more buildings on campus, such as Baird Hall and the Center for the Arts. There is also a proposal for a large off-site solar array that would cover 100% of UB's power usage. UB has been able to reduce its carbon footprint by 33% over the past years and aims to be net zero by 2030. The two 60-kilowatt microturbines in Alumni Arena were installed in 2004 to help reduce the energy consumption for maintaining the pools. The turbines provide enough power to run the pool's circulating pumps and other auxiliary equipment. Heat from the microturbines is captured in a heat recovery system to warm the pool water, bringing the overall efficiency of the turbines up to 62% HHV. The heat recovery system is capable of producing 540 million BTUs per hour, about 75% of which is used to keep the pool water between 80 and 82 degrees Fahrenheit. The microturbines reduce energy demand by about 300 kilowatts and saves UB from buying 2 million kilowatt hours per year from utilities. Although all of the power generated by the microturbines is currently being used within Alumni Arena, they are connected in parallel with the grid, so power could be exported to other buildings or facilities in an emergency situation.
For the electrical characterization of our microgrid project, we'll be using underground feeders to connect the overall microgrid in island and grid connected modes. And our primary generation of electricity for the microgrid would be through photovoltaic panels in the form of 2 solar arrays that are on campus. Our project will aim to total around 100 megawatts of renewable energy, and we will make sure that our microgrid is resilient to the cold weather environments of Buffalo as well.
Microgrid control is a necessary part for the entire grid to function as efficiently as possible, while remaining safe for customers and surrounding society. UB's North Campus currently doesn't have a centralized microgrid controller, which is why we must add one as part of our project. The particular model that we have chosen is the Cummins MGC 900, which meets all of our expectations, as well as providing an easy user interface. The MGC 900 allows us to monitor real-time information, as well as being more flexible than its 300 counterpart. This model also provides power optimization by balancing all distributed energy assets to maximize the output of renewable power and achieve the lowest total cost of energy. It also manages charge and discharge of energy storage, as well as automatic starting and stopping of generators based on load demand. This microgrid controller logs all data internally and allows you to access this data remotely, as well as make changes to the system remotely.
Hello everyone, this is Yadavan Subramanian. I'm going to talk about the information technology and telecommunication infrastructure characterization. Why we need the information technology for a microgrid. Real-time reliable information and communication system play a critical role in smart grid operation and management. In order to achieve this high level of efficiency in microgrid communication system, the information communication technology infrastructure in the smart grid environment needs to be reliable, highly available, scalable, secure, and easy to manage. We will be using 3-layer communication architecture for our proposed microgrid system. The wide area network will be used for the control center with the transmission and distribution substations. The wide area network consists of many communication points like smart meters, remote terminals, phasor measurement units, and other sensors for remote automation purposes. Field area network is responsible for level of distribution subareas and control of information flows between wide area network and customer premises networks. This type of network provides a large number of smart grid services such as smart metering from the customer side to the control center, load management, and distribution automation. Home area network will be used for the microgrid. This can interact with the field area network, wide area network. Home area network mostly includes automation appliances and smart meters. In addition, it can be made up of energy sources and storage. This figure shows the simplified layered communication architecture. Wide area network covers the generation and storage of this microgrid. Field area network covers the distribution system of the microgrid. And the home area network covers the customer, where the University at Buffalo in our case. Communication system and microgrid. Blackout is the major issue for microgrid. When the communication system fails, we may experience a power outage, and when the power is not there, we may experience the communication system failure. Disasters and severe weather conditions can cause the power outage and communication failure. In some emergency circumstances, the communication network can experience overload situation due to the high demand, and this can cause the communication system failure. In order to avoid this issue, we are going to use the external battery storage power input for our communication system and the controller system. In that way, we can avoid the power outage for our communication system. If all the microgrid components get to communicate with each other, we can avoid the microgrid blackout. We are aiming to use the 5G based public land mobile networks to give the most reliable communication for the microgrid system as a secondary communication system, which can help in blackout recovery situations.
Much of the value offered by the microgrid will be through ancillary services. Such services permit the system to perform many extra functions, including selling excess power to generate revenue. It permits voltage support during brownouts. It creates the ability to power loads that require large surges of power to start up. It functions to provide power during periods when energy demand is at apex, thus reducing the higher fees associated with high demand. Moreover, demand response programs like synchronized reserve helps to supply electricity under scenarios where the grid has unexpected need for more power on short notice. Users who are part of the program can earn money for being available to use less energy on short notice when the grid is stressed. This helps preserve the environment while also adding stability to energy prices for ratepayers. Because of the utilization of demand response programs mentioned previously, the microgrid will be able to lower costs paid by consumers in the area while also providing stability and resilience to the grid. Moreover, with SUNY support, the installation of the microgrid here and on other SUNY campuses will help bolster New York's wider objectives, including programs like New York Rev. This will help New York maintain its status as a leader in renewable energy generation. Moreover, some aspects for consideration during installation includes the amount of space required for the addition of new components for the microgrid. This, along with infrastructure needed to protect the components, may impede some of the beauty offered by the campus, but it may also hamper the ability to navigate around campus compared to how students do now. As mentioned before, New York State is a national leader in renewable energy generation, but titles related to on-campus generation of renewable energy usage by college campuses belongs to academic institutions outside of New York State. This microgrid will allow SUNY to compete with colleges like the University of Minnesota and the University of Missouri, who both generate over 7 MMBTU on their campuses on a per-student basis. All this, in combination with local energy optimization and lower emissions associated with local generation, will increase New York's ability to meet its energy goals. Moreover, to achieve such results, some hurdles will need to be overcome during installation. For example, Amherst requires permits for any removal of forestry, addition or removal of electrical wiring, and for the construction of buildings and or sheds that will be used for storing components, as well as maintenance equipment.
In order to complete this project with the least amount of hiccups, it's extremely important to consider all legal viability. The structure of ownership for this project will be a combination of co-owners between participating companies. UB will be primary owners, while companies like National Grid and Solar Liberty will be secondary co-owners. With UB as primary owners, all decisions must be made through the SUNY Board of Trustees, who make all major funding decisions for projects on campus property. Since contractors will be installing equipment on UB property, they must be compliant with UB's codes, rules, and regulations. In order to do this, contractors must abide by and be subject to inspections through UB's Facilities, Design, and Construction Division. Finally, in order to protect privacy rights of the microgrid customers, user data will be encrypted and secured, with the only exception being companies listed as part owners of this project.
In terms of the financial viability for our microgrid, we have a projected cost of about 1.9 million for the total project, and our revenue stream will be dictated by how the campus will utilize the dynamic nature of the microgrid. Operational costs for our solar array arrangement will be about $2.50 per wattage used. Overall, our financial plan will be mainly focused on saving as much as possible on the costs and getting as much usage from the utility for the campus.
Facility and customer description. We are building this microgrid to serve University at Buffalo North Campus. The facility that the microgrid will serve is considered a large commercial facility. The facility is a large-scale institutional facility, contains many sub-buildings. The weekly power consumption for this facility is 2,726 megawatt hours, and the typical summer peak load is 23 megawatt. The cost analysis of building the microgrid is essential. Through the cost analysis, we can identify the building cost of the microgrid, maintenance cost, and the operational cost. Our microgrid facility approximately have a lifespan of 30 years. After that, it need to be remodeled or need to be upgraded. We calculate the cost of the microgrid system through the sectors storage, equipment, labor cost, and operational and maintenance. Project cost. For our microgrid proposal, we are using the existing generation. We plan to use the energy storage unit system built by Honeywell. The energy storage system are capable of storing 500 kWh to 4 GWh. For our microgrid, we need 10.6 megawatt energy storage. This battery storage uses lithium-ion based cell chemistry technology to build the system. Some of the benefits of this energy system are reducing the carbon footprint, operating battery energy storage system as a spinning reserve in microgrid. and reducing equipment damage that can occur due to the outages and seamless transfer between the grid and battery energy storage system. The average cost of this battery storage for the 1 kilowatt system is $625 according to the US Energy Information Administration. The approximate cost of our energy storage system will be around 0.8 millions. We will have some operational and maintenance cost for our microgrid. The microgrid needs to be maintained and communication system need to be updated on a regular basis. We will need an electrical engineer technician to maintain the grid. The estimated salary for the technician will be around 60,000. Distribution is the major part of a microgrid proposal. We are going to use the existing underground cables for our distribution. We plan to use the AWG4 cables for any external microgrid distribution needs. This cost around $1.63 per foot, and the total cost will be vary upon the installation. We expect to need around 10 miles of cables, so the final cost will be around $0.08 million. We are using the MCG 900 Cummins as our microgrid controller. The average cost of the microcontroller in the United States is $155,000. From our cost analysis, we found out the storage cost is 0.8 million. The operational and maintenance cost for is 0.06 million. The fuel cost is 0.23 million. Equipment cost is 0.095 million, and the total cost comes as 1.19 million for a year. Characterization of distributed energy resources. The renewable energy resources we are using for our microgrid is solar energy. We plan to connect the existing 4 solar energy generation arrays to our microgrid. 11.2 kilowatt-hour of energy gets produced from those solar arrays for an year. The natural gas-based microturbine in Alumni Arena generates 112 kilowatts. 1,000 cubic feet of natural gas needed to generate 1 kilowatt-hour electricity. The natural gas microturbine needs 120,000 cubic feet of natural gas. The average natural gas price is 6.23 per 1,000 cubic feet. So the total cost of our natural gas need will be 0.23 million. Capacity impacts and auxiliary services. Peak load generation numbers help to identify the electricity demand when the demand is at its highest. For the University at Buffalo North Campus, the typical winter peak load is 32 megawatts and the typical summer peak load is 23 megawatt. When the microgrid works as an islanding mode, the summer peak load is 9.05 megawatt and the winter peak load is 12.6 megawatts. Emission rates are the biggest consideration in power generation and distribution. Comparatively, the microgrids are very low in emission because we use renewable energy resources for our microgrid. We can use the natural gas fuel microturbines at Alumni area which can emit flue gases like carbon dioxide and nitrogen oxide, which are very harmful to our environment. We need to use the flue gas treatment to reduce the amount of emitted pollutants. For that, we plan to use electrostatic precipitators and scrubbers which can remove about 90% of the pollutants. Maintain service during a power outage. Power outages can happen for 4 major reasons such as distribution failure, transmission failure, supply shortages, and public safety power shutoffs. The microgrid communication system needs to be on all the time to operate microgrid for more effectively. When a blackout situation happens, the communication system needs to be remain active. In order to do that, we need a backup energy storage system. We need to connect the communication system with our Honeywell battery storage system. Our battery storage system can continuously give the power for up to 48 hours. In an extreme electricity blackout stages where the power gets disconnected for more than 1 day, we need to cut down the power supply for certain buildings by analyzing the importance. We are using the underground cables for our distribution system. If the distribution cables failed, we may need to inspect and fix the cables. For that, we may need to spend cost for the labor and for the new equipment cables. Thank you.
The following services will be supported by the microgrid in both parallel grid connected and emergency island modes. Water services will be supported at 100% capacity with an estimated maximum of 35,000 people at any given time. Housing services, which serve an estimated 6,500 people, will be at 100% capacity at any given time. In an emergency, streetlights in the radio transmitter building will be supported at full capacity. The radio transmitter building will be supported in case of necessary emergency broadcasts. The microgrid will not support UB Police Department, and emergency services will need to be coordinated with Amherst Police Department.
For our microgrid proposal, we need to use some standard and codes. The first one we use is IEEE standard, the guide for design, operation, and integration of distributed resource island system with electrical power systems. This standard provides an introductory overview and addresses engineering concern of distributed resource island system. It is relevant to the design, operation, and integration of distributed resource island system. Implementation of this guide will expand the benefit of choosing distributed resources by targeting improved reliability and building upon the interconnection. This includes the ability to separate from the interconnected part of the area electrical power systems while providing power to the islanded electrical power systems. This guide includes the distributed resource interconnection system and participating electrical power systems. The other code we're using is fire codes, the International Fire Code from NFPA 1. PV systems present special consideration for firefighters and first responders. Potential system hazards including tripping, structural collapse due to the extra weight from the system, fire spread, inhalation exposure to toxic materials, electrical shock, and other hazards if battery energy storage system are also present. Fire codes are designed to minimize the risk of fire, protect public health and safety, and safeguard firefighters and other emergency responders. In addition to the International Fire Code, the National Fire Protection Association produces NFPA 1 Fire Code. Ideally, fire codes should strike carefully balance of ensuring the firefighters can efficiently and safely do their jobs while at the same time allowing consumers to maximize their PV potential. The other code we're using is IEEE code, recommended practice for utility interface of PV systems. This standard recommends practice contain guidelines regarding equipment and functions necessary to ensure compatible operation of photovoltaic systems that are connected in parallel with the electricity utility. This includes factors relating to the personal safety, equipment protection, power quality, and utility system operation. This recommended practice also contains information regarding islanding of PV systems when the utility is not connected to the control voltage and frequency, as well as techniques to avoid islanding of distributed resources. Thank you.